Address reuse is a normal part of network life. Devices join and leave, virtual machines spin up and down, cloud instances are provisioned and destroyed, and the addresses they used are recycled. But reuse is more than just housekeeping. It shapes reachability, security, observability, and user experience. Understanding how and why addresses are reused helps explain many operational headaches and design trade-offs that network engineers face every day. At its core, address reuse means that the same numeric address can be assigned to different endpoints at different times or in different contexts. This can happen in many places, within a local DHCP pool, across virtualized tenant spaces, or when public IPs are reclaimed and reissued. Reuse is essential because address space is finite, operational costs are real, and dynamic scaling benefits from automated allocation. But reuse also creates statefulness. Systems, logs, caches, and user sessions often assume continuity that reuse breaks. How does reuse happen in practice? In typical IPv4 networks, DHCP servers manage pools of addresses and assign them to clients for limited lease periods. When a lease expires or a device releases an address, that IP can return to the pool and later be assigned to another device. Cloud platforms behave similarly, but at much larger scale. An IP attached to a terminated instance is returned to the provider's pool and may be attached to a different customer later. Overlays and container networks also recycle addresses inside namespaces. NAT and port multiplexing intensify reuse on the public side. Thousands of private addresses may share a single public IP via translation, so reuse at the public-facing boundary is deliberate and frequent. Why does address reuse matter? First, it affects correctness. Logs and monitoring that identify actors by IP can confuse one device with another over time. Troubleshooting that relies on historical IP-to-host mappings can mislead operators if reuse is not tracked. Second, reuse impacts security. Reassigning an IP to a new tenant or user without revoking cached credentials or sessions can allow accidental access or enable replay attacks. Attackers can also inherit reputation from previous occupants of an address, causing false positives in threat detection. Third, reuse influences usability. Long-lived TCP connections and application sessions break when an IP is reassigned, causing apparent failures for users. Finally, reuse shapes design choices, whether to use long leases, employ sticky assignments, or decouple identity from address through higher-level identifiers. There are important features and trade-offs to understand. Lease duration is central. Longer leases reduce churn and provide stability for sessions and logs, but waste scarce address space. Shorter leases improve utilization, but increase the frequency of reassignment and the chance of transient conflicts. Reservation and DHCP, static mapping, offer predictability by tying addresses to hardware identifiers or instance IDs, but they reduce pool flexibility. Overlays and NAT hide reuse from external observers but introduce complexity. They preserve internal uniqueness while collapsing external visibility. Another crucial feature is the existence of cooldowns or grace periods. Many systems implement an interval during which a recently released address is not immediately reassigned, reducing risks of collision or stale state. What are the practical implications for network behavior and operations? First, observability needs to account for reuse. Correlate IP logs with DHCP lease records, instance IDs, or authenticated user tokens to map actions to the correct entity. Effective logging includes timestamps and lease identifiers, so historical queries remain meaningful. Second, security controls must be robust to reuse. Invalidate sessions on address release, revoke cached credentials when appropriate, and avoid relying solely on IP for trust decisions. Implementing authentication tied to stable identities, certificates, tokens, or device IDs sidesteps many reuse risks. Third, application design should tolerate address churn. Use reconnection strategies, idempotent operations, and session tokens that survive IP changes where possible. Fourth, Operational policies should balance lease length, reservation practices, and pool sizing to match workload characteristics. Mobile clients benefit from longer leases, ephemeral cloud workloads favor short leases, combined with tagging and metadata for traceability. There are also common pitfalls to avoid. Don't assume an address uniquely identifies an entity forever. Avoid building permanent audit trails that use IP alone. Beware of stale DNS records or firewall rules that reference addresses without accounting for reuse. In multi-tenant environments, be cautious when returning public IPs to a shared pool without clearing reputation data or access controls. And don't forget the human factor. Educate teams that an IP seen in logs may not represent the same physical device next week. Address reuse is not a flaw to be eliminated. It is a necessary strategy for efficient addressing and scalable operations. The goal is to manage reuse consciously, choose sensible lease policies, provide mapping between ephemeral addresses and stable identities, instrument systems to correlate events across address changes, and design applications that degrade gracefully when addresses change. When managed well, reuse enables elasticity, conserves scarce address resources, and supports automated provisioning. When neglected, it creates ambiguity, undermines security, and complicates troubleshooting. In short, address reuse is a routine but consequential behavior of real networks. It balances scarcity and scale, and it demands that we separate identity from location in our designs. Recognize reuse, track it, plan for it, and design systems so that the reassignment of an IP is an operational detail, not a catastrophic event. That is address reuse.